Now we're going to do something fast. So back to my share screen. All right, File, New. Okay. All right, so I'm going to drag a voltage source. I'm going to magnify this a little bit because I'd like a little bigger image. And I'm going to drag out 3 resistors. And I'm going to rotate this particular one. And I'm going to put a ground in here. So let's go ahead and put a ground over here. Deselect. And I'm going to connect this guy to this guy. I'm going to connect this guy to this guy. I'm going to connect, hover, hover, hover. Come on, be nice to me. Be nice, hover and connect. Good. Deselect and hover and come over. Good. And do one more. Hover over and connect. Oops. Eliminate. All right, it's gone. I'm going to double click on this guy and I'm going to make this guy 300. I'm going to make this 3,800. Double click this guy and make this guy 2,100. Double click this guy and make this guy 7,100. 7,100. And double click this guy and I want to change the frequency to 2.6K. And I'm going to change the voltage. I want the voltage here to be 15 volts. Boom. All right. Pull out your paper. Let's do a VIR very quickly. VIR. Plus
Professor, is this VP or VRM?
VP.
Thank you.
Thank you. Remember to double check, recalculate your current more than once. Make sure your RT is good, because if either one of those is wrong, we're going to be crying the big tears. All right, the calculation's done. Now, let's go ahead and place my probes. So I'm going to do a voltage probe there. Grab another voltage probe, put it there. Grab another voltage probe and put it there. Cool. So 3 voltage probes were fine. And everything looks good. All right, I want to do a split. This can be narrower. This can come over to here. Okay, and let me run this. Waiting for data. It's now run. While it's running, I've got too many cycles on my display. Change to something that's more readable. Pause it for a moment. Yeah, that's pretty readable. That's good. Very good. All right. While this is here, my cursors come over to cursor on the y-axis. And before I pop my cursors in place, we need to have a target and understand what kind of voltages we expect to see. For a 15-volt source, who would like to volunteer the voltage for R1? How much voltage do we calculate for R1?
4.37 volts.
Harpreet says 4.37. Yeah, that's pretty close. I get 4.38 because I'm using all memories, but that's fine. So Harpreet, good job. 4.37, 4.38 volts. I'm looking for a VR2 from another classmate.
2.42 volts.
Ephraim says 2.42. Ephraim, 2.42 volts for VR2 is correct. I'm looking for a volunteer for VR3.
I got 8.17 volts.
Benjamin comes in. Benjamin, there you are. Benjamin comes in at 8 point what?
8.19.
8.19 volts
Volts.
is correct. Okay. Now, those are the voltages across each of the resistors, just doing a simple one of these, a simple VIR chart. Doesn't take long for us to do. We've done this many times. Now, how about the voltage at A? How about the voltage at B? And how about the voltage at C? These are very specific points. The voltage at A would be your PR1. So who volunteers a voltage at PR1?
I got 15.
So Luis volunteers a voltage at PR1 of 15 volts peak, and that would be correct. Who would like to volunteer a voltage at probe number 3, PR3? Probe number 3. Who would like to volunteer a voltage at probe number 3? If you're trying to speak and your mic is muted, I can't hear anything. Nobody can volunteer a probe voltage at PR3?
8.19 volts peak.
Just excellent. There, it turns out, my friends, that probe at point 3 is the voltage of the R3 volts, R3 resistor. Okay, so the probe at point 3 is the voltage across R3 to ground. Now, a more interesting one is how much will the voltage read at probe number 2? Who can volunteer that? You should have 10.62 volts. Okay, you should have 10.62 volts because that is the sum total of voltage across R2 and the voltage across R3. Those two add up to 10.62 volts. So your VA is at 15. Your voltage at point B, your second probe, is at 10.62. And your voltage at point C, which is probe 3, is at 8.19 volts. With that information written down, I will now move the cursors to confirm. All I need to move is just one cursor. I don't even need cursor number 2. I'll just use cursor number 1. Without using the cursors, just looking at the vertical scale on the left-hand side, where do you see that green waveform peaking at? Is it peaking on a line right here? And is it associated with this 15-volt marker on the left-hand side? Yeah, it's 15 volts just by virtue of reading it right off the graph. The other two waveforms, however, are harder to read off the graph because they don't line up with any of the graph markings. Here's where you do need a cursor. So I'm going to grab the cursor and I'm going to move it above the light blue. And we expect what, 10.62? Let's see what happens here. Move it right to there. Cursor number 1. I expect 10.62. What do I get? 10.676. Pretty darn good. Are we happy with that? How about the voltage across the probe number 3, which is the dark blue waveform? We predicted 8.19 volts. I'm going to move this cursor down to the top of the dark blue waveform. And we expect 8.19. What do we have? 8.26. Pretty darn close. We're happy. Okay, in the real world, we're happy because there's some tolerance. Even in the simulators, there's some tolerance. Are we good with confirming the voltage values? Now we want to confirm the time. Okay, and to confirm the time, I have to change my cursors from the y-axis to the x-axis. And I'm going to move C1 over to here. Best as I can, right there. So what I've done is I've moved C1, and do you see a little circle that follows the intersection of C1 with the green waveform? Do you see that little circle riding along the waveform? I want to move this until that circle goes all the way down to the 0 line. Right, went below. Move it right. Had it for a moment, and then I moved it. Okay, right there. Whew. All right, now I'm going to move the second cursor right here. All right, and the time difference between these two, my delta x is given right here. My delta x is my difference of time between the two. It is given as 384 384.96 microseconds. That is the time for one cycle. Key that into your calculators right now. Key in 384.96 96 micro, so second exponent negative 6, and enter that. While you have the number of microseconds, the time entered, can we immediately calculate frequency by reciprocating this number? So hit reciprocal key and hit enter. And what do you calculate? Your calculator should show you 2.5976. Is that pretty close to 2.6 kilohertz? Wasn't 2.6 kilohertz our set frequency? Does the oscope here show you the reciprocal of 1 over x as 2.5977 kilohertz? Is that pretty darn close to your set frequency of 2.6 kilohertz? This is a remarkable free online oscope circuit simulator. Everything we've done in TINA, we can do here and more. Okay? So you really can't appreciate this until you've done the TINA circuits. But once you've done the TINA circuits, you say, oh man, now I can do this much more because I can't do this in TINA. All right? Any questions about this? We've gone through 2 examples with this particular guy. I'm really excited that we had the time to do this. Any questions? Okay, so what should you do between...
Wait.
What?
So I got lost on the 3 probes that we made.
Yeah. You know where I got them from? You want to see where I got them from? I'll show you where I got them from. Okay, let me hit stop because this is... Okay. So I have to stop the simulation. So the probes came from our menu on the far left, and the probes are this green dot at the top. So when I click this guy, I can select a voltage probe, a current probe, other kinds of probes. I'm just going to select voltage. So I click and yank this guy out, and I can place this anywhere. So now I've grabbed the 4th probe, and now I've got probe number 4. So that's where I grabbed the probes from. Did that answer your question, where they come from?
Or not really, because then we had predicted peaks. Was that what was said earlier?
Yes, we had predicted peaks, which are right here. Okay.
Not from the VIR chart.
Okay. So the predicted peaks. Yes. Okay. I understand what you're exactly what you're getting at. Let me help you out with this. Let me add one more thing to this computer that I didn't have a moment ago, and bring in this camera so that we have this here. And let me switch the video from the wrong mouse. That's what happens when you have 2 computers on the desk. Okay. Let's go to here, and let's go to here. Okay. Can everybody see my VIR chart? My VIR chart should look like your VIR chart, or your VIR chart should look like mine. You have your you have your resistances, total, current. You double check the ohms total. You double check the current total. Then you fill in the current column. After you fill in the current column, you multiply, and you end up with these voltages. So are we happy with these voltages so far?
Yeah.
Done. Now, we want voltages at specific points with respect to ground. Now, in order to get voltages at specific points with respect to ground, we have to look at our circuit. So our circuit was AC source. So here will be a resistor, a point. Here will be another resistor, a point. Here will be a last resistor, and we have ground down here. So we said that we would have 4.38 volts here, 2.42 volts here, and 8.19 volts here. This goes to the very heart of what we did last week in terms of our labs, when especially this, I think there was circuit G, because you had to know with confidence how much voltage you had, very specific points with respect to ground. This point will be A, this point will be B, this point will be C. So if I am looking for VC to ground, and the top of this is positive, negative, positive, negative, positive, negative. At point C to ground, where's my ground? Way over here. Is my ground also here? Same point, yes? So between C and ground, I have my red probe here, I have my black probe here. What do I expect? What do I see between these two? Don't I see the 8.19 volts? So my voltage at point C is going to be equal to 8.19 volts. So VC equals 8.19 volts. Now, how about voltage at point B? The voltage at point B says that I have to have my red probe here. Where's my ground? Still over here. Do I have voltages between the red probe and the black probe? Clearly I do. And so what do I have between the two is I have
The sum?
the sum of the two.
Okay.
And the sum of these two worked out to be the 10.62. 10.62 volts, so that's 10.62 volts. And then the voltage at point A means my red probe goes way over here. Well, what is the sum of all three? Isn't that equal to my 15 volt peak? Okay, so that's where these voltages came from. Okay, voltage at the first probe, voltage at the second probe, voltage at the third probe came specifically from our exercise in circuit G last week. And knowing what voltages we expect at specific points, our reference is ground. All we have to do is keep our black probe at ground and just move our red probe from here to here to here, which on our oscilloscope, we did this way. Wrong mouse. I keep grabbing the wrong mouse. Come back to, so if I go back to run this and my cursors, I readjust this for y-axis and then I stop. And my cursor, I move this up to here. I have 14.959, very close to 15. If I move my cursor to the top of the light blue, I expect something like 10.6, and I get 10.659. And I move this here, I get 8.19, I hope. And let's see, stop right there, and I get 8.1957. So the cursors, because they're straight lines across, they touch the tippy tops of each of these waveforms, we're able to confirm what's at point A, what's at point B, and what's at point C. So this is a really remarkable piece of software that we can very quickly find our way around doing what we need to do.
Okay, well, that definitely helped. I think I got confused on the schematic side.
Yes.
Where you paused it, I was looking at those numbers, but
Yes.
they fluctuate because it's AC. So I was trying to compare those numbers to the predicted numbers, and they weren't matching at all.
No,
Yeah.
they
That's
weren't.
my mistake right
Yeah,
there.
until I stabilized and stopped everything.
Yeah.
So right now, the waveforms conform to our calculations of our VIR. So if you stay with VIR, you're rock solid with all of this.
Okay. Thank you.
Okay. No, I appreciate the question. I'm glad you asked. Any other questions?
Professor, how do you zoom out? Because I zoomed in too much and I can't zoom.
You'll have to play with it. I think
Sounds good.
you have to be. Let's see. I am here, and then I go ahead and stop. Yeah, you'll have to play with it. I don't have a fast answer for that. That if you change your scale vertically or horizontally, I know on the run mode, I can change my time base, and my time base allows me to have not enough cycles on display like this. That's not enough cycles, I need more. And then so if I change my time base here, now I've got too many cycles on the display. So while it's in the run mode, I change it to here, and I've got a very comfortable amount of sine waves on the display with enough spacing that I can do my measurements with some degree of confidence. Now, if you've got your vertical scale changed, you're going to have to play with that. This is new for me also. I'm really used to playing with regular multisim.
Sounds good. Thank you.
So what I'm going to do here is, since we've done so much work, I'm going to do a save as. And on the save as, this is again AC. And this is 3R, and I'm just going to type IMA -2 because I've already got another AC3R. And now you save it. And then from here, you can do screenshots and then paste into a document and upload and send it to me.